going to cover the Kirchhoff circuit law from Q plus, and the law says that the sum of the current entering a junction is equal to the current leaving the junction. So this means from this example we can see that I2 and I3 are entering, so they are positive, and I1 and I4 are negative because they are leaving the junction. So that's how we set up the equation for Kirchhoff's first law. Pretty simple. Now from second law we can learn that the sum of the voltage in a closed loop like this is equal to 0. And to set up the equation we need to know that from source like this one the voltage is positive because voltage is generated, while in the resistors the voltage is negative because there is a voltage drop, which means the voltage is decreased. So we can say from this equation that V1, V2, V3, which is for the resistance, are of the same sign, while V4 from the source is a different sign. Now let's have a look at practical problem. We can see this circuit is made of two loops, and we're gonna set up three equations to find out the current I1, I2, and I3. So using the Kirchhoff first law, we can say that I1 is equal to I2 plus I3 because I1 is entering and I2 and I3 are leaving. And then from using the Kirchhoff second law, and if you look at the first loop, this one here, we can see there is a source E1 and two resistors. So the source is one side of the equation and the other side equal to R1 times I1 plus R2 times I2. So that's how we set up the second equation. Similarly, for the second loop we have voltage 1 and voltage 2, so we sum them and equal to R2 times I2 and R3 times I3. This is because these sources are positive and these two resistors give negative voltage. And as I said before, this is the equation that we set up. This is the final equation, so we solve algebraically this equation we made and we find out the value of I1, I2 and I3. And some of the question they ask you to find the energy lost or gain. For example, if they ask what is the energy gain from the source, you just do E equals Q times V. So that's the formula. Again, E equals to Q times V, and you find the energy at the battery. Sorry, I mean in the source. And for the battery, not for the battery, for the resistance, we just do E equals Q times V, but this time it's like energy lost. So that's all you need to know for this chapter, and thank you. So welcome back, and this time we're going to cover the second chapter of this section, and we're going to look at the series parallel connection, the equivalent resistance, which means how to find the total resistance of a circuit when there are plenty of them, and the voltage divider rule. So this one I need to understand why this is plus and minus, so I'm going to skip for now, and let's have a look at the equivalent resistance. It's basically a circuit made of multiple resistance, and our goal is to find the total resistance. And here there are three questions that ask you to how to solve this kind of problem. So the first one, we have 9 and 7 ohm, so we just sum them because they're in series, and then this becomes 16. So we just draw them again and it becomes 16. Then we do 16 plus 4 but in parallel, and then once you find that, we can do 6 and 12 because they're in series, and then at the end we can do 18 and this one, the total of this one, to find the total resistance. And this is how you solve. It's very simple and straightforward. You just carried, and this is the main formula. I mean, main thing is remember for series and parallel. You need to remember the voltage in parallel is same, and for equivalent, the current is like it change every time there is a junction. For equivalent resistance, the R equation is Vs over Is equal to R1 plus R2, and for parallel you just do like this, which is quite and these are the problem they need to solve. They're very simple, and in order to solve this kind of question you just need to watch a YouTube video that I found. I'm going to show you in a bit. For example, this one looks this question part B looks complicated, but it's not. You just the basic rule is start from the right and then come to the left. So start from the right and finish to the left. So in this case we have 35 and 40 ohms, so these are in series because there is no node in between them, so we just sum them, and voila, we have a new resistance, which is 40 plus 35 each is 75. So 75 with 50, which is in parallel because there are two nodes in between, so use the parallel formula to find the resistance, and then again you keep simplifying, simplifying. And and to solve this problem, we're gonna watch this video here that explains step by step how to find the total resistance. And what's interesting is that it like a breakdown, and this is the example that they give you. So I must, or you must, do it. And from this three triangle, they can see that all of three are like parallel. So it's very simple and straightforward. So keep doing it, and you'll be amazed about how easy is this question. And also one more thing is the voltage divider. So basically the voltage is divider is used to reduce the voltage by the use of multiple resistors, so it can be adjusted. These things can be learned in this video. Basically it's saying that the V in is V out, and so 1 volt is the input, 1 volt, and 80 ohms is the resistance. So the output, of course, is 0.2 volt because 80% of the voltage was being dropped or taken by this, and that's how you carry on. And this is the general formula. So V out is equal to V in. So the V out, the output voltage, is given by the product between the input voltage times by the bottom, the ratio between the bottom and the bottom plus the top. So just remember, memorize it, and you'll be fine. And these are many examples, and you know that power are like wasted in their some power are like wasted because of the resistance, and this is the formula. So it's V squared over R. In this case we have 2R, so just sum the R, and this is like how much energy have been power, sorry, has been wasted. And that's pretty much all you have to know. And one example of this is the volume controller, and this is a problem we need to solve, and that's it for this chapter. Thank you so much. We'll move to the next one. So welcome back to part 3 of this video tutorials. Stop. So welcome back to part 3 of this tutorial, and we're going through the sinusoidal source. And basically what it does is basically converting voltage, current, and other variables in terms of sine and cosine function. And as you can see, this is the general formula where A is the amplitude, sine is the sine, and omega is the angular frequency, and omega is given by 2 pi f, where f is the normal frequency, and phi is the initial phase, or simply phase. And there are things that you need to know for the sinusoidal source. One is the period. So period is the amount of time it takes to complete one full oscillation of the wave, and frequency on the other hand is the number of oscillation per second, and it's the reciprocal of the period, and it's a 1 over t in fact. And we have the angular frequency is the value of the frequency expressed in terms of radians per second. And phase is quite complicated because phase is a quantity that expressed in radians of the time shift of a sinusoidal. So I don't really know the meaning, but so if you have phi equals 2 pi, it means that it's moved forward by one whole period. And then we have the lead and lag. So basically what it does is that if current has a lower phase angle than voltage, means that we have a lag. But if the current has a higher phase angle, it means that we have a lead. So lead when you have higher phase angle for the current, and lag when you have a lower phase angle for the current compared to the voltage. And there is a fundamental principle of passive linear circuits, which basically says that in engineering you get what you put in. So it means that it implies that if you put sinusoidal input, you will produce a sinusoidal output. And this only works for passive linear circuits. So what you put is what you get out. And in terms of sine and cosine, you need to remember that whether you write in terms of sine or in terms of cosine, it doesn't make a difference. It's the same thing. And in fact, this is the formula to convert from sine to cosine and vice versa. And the problem with the sinusoidal source is that the value of the sinusoidal voltage continuously change from 0 up to a positive peak, so it's continuously changing. So as a result, we need to find an average, and this average can be found using the root mean squared, and this is the general formula for the to find the RMS. And in order to find this, you need to carry out three simple calculations. The first one is to find the square of the function, of the waveform function, and then, as seen in the formula, and then find the average and the resulting function averaged over time. So needs to be averaged over time. And thirdly, the square root of the result obtained. And this is how you get the RMS. But for our case, it can be simply, the whole equation can be simplified to V max over square root of 2. And I'm not sure what is A, but it's basically what it's saying is that V max over square root of 2 will give you the RMS. And RMS is quite effective to find the actual the effective current and voltage between the AC alternative current circuits. And one thing to remember is that once you find the IRMS and VRMS, the average power can be found within this formula, which is pretty straightforward. And that's all you need to know. And here is a very good example where there is a circuit. I assume it's a AC circuit, and AC circuit is written where the current is written in this form: 5 cos 300t plus 20 degree. So where 5 is the amplitude, 300 is the 300 is the angular frequency, and 20 degrees the phase. And the current, from the current you can obtain the omega, the angular frequency, and is, which is the phasor. So current in terms of phasor, where 5 is the amplitude and 20 degrees the degree. Okay, so this is like the complex number. And for the capacitance, inductor, and resistance, we need to find the impedance. Impedance is given by, for the capacitor, 1 over JWC, and 1 over J is which is simply just minus J, which gives minus J over 1.5. While for the inductor, it's a JWL, well, L is inductance, and it simply do the same thing. And Z3, for Z3 resistance, just the same, the impedance. And just to remind you, impedance is the how hard, it's like friction, so it's resistance to the flow of current, so how hard it is. And also I did like one explanation from Quora, which is explained pretty well. So what is impedance? You can think of impedance as a more generalized version of resistance. So it's a general form of resistance. It's useful for working system where we have look at how circuit performs over time. So it's useful with systems that where you look how the circuit performs over time. And we represent impedance as a complex number where the real part is the resistance and the imaginary part is called the reactant. So that's all you have to know. Thank you very much. So now we're moving to the complex number. For complex number, we have this lecture slide. Basically, you need to know that the complex number is made of real part and imaginary part. And just remember that j squared is equal to -1, and j only equals to square root of -1. And there is a complex plane, and there are various ways to write the complex number. One is to write in the Cartesian form, where z is a complex number equal to x is the real part plus j and y, which j is the imaginary part. And you also can write in the polar form, and which gives you this equation here. So z is equal to r times r is the magnitude and cos phi plus j sine phi, which is the the argument. So r is the modulus, the magnitude, and this part is the argument. You can also write in the Euler form, which means in terms of as exponential as a function. So r is against the magnitude, and ej by theta, and theta is the phi is the angular the argument. So that's all you have to know. And just remember, for operation, for summation, just do the vector sum of modulus and argument, while for multiplication you do multiplication of the magnitude and summation of the argument. And now we're going to talk about phasors. So phasor is a crucial component of our course because it is a representation, is a way to represent sinusoidal function. And there is a definition which is quite long. We say that phasors is a time-dependent complex number represented by a vector rotating about the origin in a complex plane, which projects the sinusoidal function. So this is the definition that we have here. I'm not sure if you have to learn it by heart, but we carry on. And this is the general form where A is the amplitude, omega is the angular frequency, and t is the time, and that's the phi usually is the angle, and the Euler's identity. But all you have to remember is that the phasor can be written as this, where A is the magnitude and theta is the angle. And sometimes you can be asked to you can be asked to calculate the summation of voltage written in the sinusoidal form. So look at here, it's written a phasor is a representation of a sinusoidal. So a phasor is a representation of a sinusoidal function whose amplitude, frequency, angular frequency, and phase are time invariant. So it means it doesn't depend on time. So the whole goal of the phasor is to separate the dependency of A, omega, and theta into three independent factors. This can be achieved using the sinusoidal function. And here there is let's give this example, which is not very good. So we're going to use this example. So they give you like the voltage in the sinusoidal form, Vi and V2. So the two voltage, they ask to find the resultant voltage, which is quite simple. So since the omega is same, we focus only onto the angular part, I mean only the argument. And here pi over 4, so you convert in degrees 45 and this is 15 degree. Then you convert this into phasors, because phasors needs to be written in degree and not in with pi. So you get 45 and 15. Then you do the summation. So this needs to be converted into Cartesian form, which you do, which is 20 cos 45, j 20 sin 45. So you just rewrite in the Cartesian form for V1, in the same for V2. Then you sum the magnitude 14.4 and 13.32, and you sum also the argument, which is 14.14 plus 5.18, and that's all you have to know. And there is also a good example here on YouTube about how to calculate the phase. So that's pretty much all you have to know. Thank you. Now we'll move to the last topic of this chapter, electrical impedance. So of the opposition in a circuit present is opposition to a current when a voltage is applied. So electrical impedance is the measure of the opposition of current in a voltage when voltage is applied, and it's the complex ratio of the voltage to current in an alternating current. So it's basically used only for AC circuit AC current, and this can be and basically it extends the concept of resistance. You know, resistance is like the real part of the complex number, and the imaginary part is basically other factors. Resistance is basically the real part of the complex number, and there are additional impeding mechanism. So you know, in DC circuit you only have resistance that who are like opposing the flow of components. There are inductance and the capacitance, and the impedance caused by these two effects is referred to as reactance, and forms the imaginary part of the complex number. The symbol is that and same unit as resistance. And the magnitude of the complex impedance is the ratio. The magnitude of the complex impedance is the ratio of the voltage amplitude to the current amplitude. The phasor and the phase of the complex impedance is the phase shift by which the current is ahead of the voltage. And that's all you have to know. And just remember, the phase of the impedance tells us the current lags the voltage by a phase. So how much the current is ahead or behind. And for each component of impedance there is like a formula. For inductor this is the formula, and for capacitor this is the formula. And just remember the separation of the impedance and is the ratio between the current to voltage, whereas the impedance was the voltage to current. This one is admittance is for current to voltage, and the unit is Siemens, and this in series is that one, so it's normal. Parallel is this formula here, and V over I. And yeah, just remember that C is impedance voltage over current. So this is like Z1 parallel term, so this is the parallel formula, and then again is in series. That's all you have to remember. Thank you very much.